Hello students, welcome to another online session for the course Computer Organization, and this session is specifically designed for the students of BW7A, and we will continue our discussion which we've left in our previous session while in designing the single cycle processor, and we've seen the basic components of the processor. We've seen the combinational as well as the sequential elements of the processor, and we've ended our discussion on the load store instructions, how those instructions are being processed, and what are the functional modules that are being used in order to manage those instructions. We will continue our discussion from this slide onward, and let us see how we're going to design that. But before that, we're going to see the requirements for the branch instruction, and we've seen that the branch instructions are the conditional instructions that has the capability to change the sequential flow of execution of your program. And how these instructions are being processed, basically, first of all, what we have to do is we have to read the operands, and definitely we have to read the operands from the register file. And if you see the format of the instruction, that is, for example, I'm using branch equal. Let me erase that. For example, I'm saying $S1 comma $S2 comma, and we've got a label. So for the first step is we have to read $S1 and $S2, and basically these are the operands that are stored in or that are held in the register file. Then the next step is to check the condition, either the condition is satisfied or not. We have to use the ALU. What we used to do is we used to subtract S1 and S2. It's just like the same way we are using the compare instruction in x86-64 architecture. So we have to perform S1 minus S2, and if the contents are equal, then we've got a result equals to 0. Our 0 flag is set basically. So basically ALU is a component that subtracts and checks the 0 output, and the flags are basically implemented in ALU. The next thing is to calculate the target address. If the condition is satisfied, then we have to move to the label, the instruction that is specified on a label. Then in that particular case, what we used to do with the target address, that first of all we have to sign extend that displacement. Now where does this displacement term comes? If you remember the format of the machine code of the branch instruction, we've got the opcode, 6 bits of opcode. Then we've got RS and RT. These are the two operands, $S1 and $S2, the addresses. And this is basically our label or the offset. That is basically of 16 bits, if you remember that. So we're gonna sign extend that, and then we have to multiply 4. So we have to use shift left 2. Why we multiply 4 with it? Because if you remember that the next instruction address, or the address of the memory location, basically we have to multiply that with 4 in order to generate the physical address or the correct address. So by left shifting the data with the quantity of 2, we multiply by 1, by the factor of 1 we are multiplying with the quantity of 2, and if you have to multiply the data with 4, we have to provide 2 left shifted or 2 left shifts. Then what we have to do is we have to add that converted data to the PC+4 in order to generate the next instruction address. And if condition goes false, then we use to follow the conventional methodology, that is the PC+4 simply. Now this is a setup. Basically we have to use that here we got a 32-bit machine code from the instruction memory, and we have extracted those 16 bits here of the label. We have sign extended those 16 bits to convert it into 32 bits. Then we have to multiply 4 with it. That's why we are using shift left 2. and it's just like rerouting the wires. We don't need any particular specific hardware component in order to shift the data. Then we have to add this updated label to the PC+4 basically to generate the branch target address. Now, how we're gonna assign that branch target address? That is dependent upon this zero flag basically, and this ALU basically performs the subtraction. For example, S1 minus S2, and decides the zero flag, and with the help of this zero flag and some dedicated control signals basically we're gonna adjust our program counter depending upon the condition is true or false, right? So these are the primary components that we will gonna use while using the branch instructions. Now how we're gonna compose those elements basically. First of all, we're going to see that our instructions are being performed in one clock cycle. That is the primary requirement for the single cycle data path. So uh, we have to ensure that all the instructions are being executed in a single cycle. So each data path element can only do one function at a time. This is the primary condition. So multiprocessing is not allowed here. If you are processing any instruction and at any particular time instant, the single functional unit cannot perform two operations simultaneously. Therefore, we use separate instruction and data memories. Basically, instruction memory is for the machine code, and data memory is to hold the data references for loads and stores. Afterwards, we have to use multiplexers to alternate data sources that are being used for the different instructions. Basically, we have to restructure or reroute the required data or the valid data uh, at that time instant for that particular instruction so that our operation is consistent and we are performing the correct operation. Now this is the basic structure that we have discussed earlier in our example, and this structure is used for the R-type loads and stores for the data path. And uh, this is not a complete diagram because we've got the the fetch unit is here in this direction. We've got instruction memory and some dedicated registers here, and the adder, if you remember that basically updates our instruction memory. If you remember that, we add 4 in it, and we've got a program counter value that is being added in order to generate the next address. So for the R type or the R loads and stores, basically we are using the register file to access the contents of the source and target register, and later for the destination register. And then we've got this ALU to perform the operation, this data memory for the loads and stores, and this multiplexer basically decides that which data should be written to the register file. We've got here two options to the two separate paths, and we have to select that this mem to reg basically is responsible of selecting the data. Either we can route the data from ALU to the register file, then we have to set the signal to 0. So in that particular case, the data is just routed back to the register file. And if we have to move some data from the memory to the register file, in case of load word, if you remember that data is moved from memory to any register, then in that particular scenario or the case, we have to set this control signal equals to 1, so that the data should be moved from here to the register file. Similarly, if you see this multiplexer, basically that is used to select the which operand should be moved to the ALU. In case of loads and stores, if you remember that we have to move the offset that is been the part of the machine code to ALU in order to compute the physical address. So the base address let me first erase that in case of loads and stores. So in case of loads and stores, we've got a base address here, and the 16-bit offset is being for sign extended to convert into 32 bits. So we have to add the offset with the base. So in that particular case, the second input is provided from this channel, and ALU computes the physical address, and that address is being provided to the memory, and we're gonna load the data from memory to the register. But for the R format instruction, then we have to provide data from this line. So we have to set this ALU source control equals to 0. So all those lines that are represented in blue, basically these are the control lines that are being provided by the control unit, and in order to direct the operations, what functional operations we want to perform, and how the data path will react according to the specific type of instruction. Right now, discussing the full data path here. So this is the fetch section that consists of the program counter, the adder, and the instruction memory. The 32-bit machine code is fetched, and definitely later on these some additional modules are added in order to update the program counter. We'll discuss that later on. Once the 32-bit machine code is being extracted, the next thing is to get the operands in order to perform that specific operation. This register file will came in hand, or will be used in that particular operation. Then we've got the ALU to process the information. Then we've got the data memory for loads and stores, and then results are written back here. So if you see that this particular operation basically controls the branch address basically. So we're gonna see that later on. We're gonna modify that with the help of this zero flag and some uh, dedicated control signal in order to update the branch address back to the program counter. So in this particular diagram, the control unit is not shown, which we will discuss that later on. So for the ALU control, if we refer to the previous diagram, that we've got a 4-bit control line with the ALU. Basically, that is used to direct the ALU, that which sort of operation which you are performing here, and the value of that basically represents that particular operation. So this table basically represents that if we set ALU control equals to 0000, then we are performing the AND operation. If we set ALU control to 0001, then we are performing the OR operation, or ALU will perform the OR operation, or the OR operation is forwarded to the main result. And similar is the case with the rest of the 4 combinations. Similarly, if you got a 2-bit ALU operational control signal from the control unit, and derived from the opcode, and this table represents that for which sort of operation we required which functional values, and for that particular functional values, what would be the status of ALU control in order to perform that particular specific operation. So if you remember that the 6-bit function bits that are in the machine code of the R format instruction, basically they are handled here in that particular scenario. Now this is the bit distribution for the machine code of different types of instructions, and which we have discussed that while discussing the sessional one and our physical sessions. Now this is the diagram that basically represents our control unit. So these are the control signals that have a specific functionality in order to decide that which sort of operation is performed and how this data path is managed and controlled. And we have designed that in our lab sessions as well. Well, that was all for today's session. In the next session, we will be discussing the different instruction scenarios integrated with this data path, and later on we'll switch to the pipeline processor. Till now, take care, students. Have a good day.